So today I'm going to talk about chemical energy storage. So I think everybody is familiar with energy storage, right? There are many ways of storing energy. So this talk is mostly about chemical. So what is chemical energy storage? It's all about batteries, right? And supercapacitors. But there are some other areas. Maybe if you want to give you, maybe I'll just so energy are in different forms, right? So you can have chemical energy, you can have nuclear energy, you can have gravitational energy, mechanical energy. So all these energy, they are in potential energy form, right? So chemical energy mostly, I think, stored in the chemical bonds, right? So nuclear energy mostly in your nucleus, in your protons, neutrons. So you have chemical energy. So also potential energy, we all know how you the hydropower, right? You move your water for high potential energy, then you store there and release it. So you can use any of these energy. Also, potential energy can be given in the elastic energy, right? So that's also potential energy. So today talk is mostly about this chemical energy. So everybody knows in gasoline. So that has very high energy content. It's all because of the chemical bonds, right? So the chemical energy is due to that chemical bonds. So, but this has the highest energy, right? The nuclear energy. So this shows you some of the energy conversion processes: hydrothermal, gasoline, natural gas, nuclear power, wind. Actually, in wind power, mostly we are using kinetic energy of wind particles, right? So all these energy forms. So I think this talk I want to give little, I think everybody is familiar with these units. So energy unit, typically we use joules, right? Energy, or power is given in watts. I think these are very important, these units to understand. So then sometimes in large energy power, we use megawatt, and energy is kilowatt hour. So I think this is, in this battery talk, these units I want to really emphasize you. Charge Q is typically current times time, right? So this is Coulomb, is in ampere times seconds, right? So, but in battery technology, usually we use this, your charge is given in milliampere hour. So it's the same thing, right? Current and time, that's energy, sorry, charge. So now if you want the energy is what? Charge times voltage, right? So that means if you, this is typically comes, people use energy in terms of, we can write watt hour. That is energy, right? What is power? Oh, that's another, right? Power is your energy with time, right? So this means your joule per second is watt. So, but typically in batteries, energy is, so that means joule is watt times second. But in battery language, most of the time energy is written as watt hour. It's like watt times second. But you will see watt hour. Then if you want power, mostly you are talking about simply watts. So please remember this one. So this will come throughout the, it's not very familiar unit, right? So that's why I wanted to put this one. So if you look at different type of energy storage, we can have flywheel energy storage. Already these are in commercial stage. I will show you some of them. Supercapacitors, they use in power energy storage. Superconducting magnets, they are used because you can store energy in the superconductive stage and release energy under normal state, right? So that way you can. This is also in commercial stage. Compressed air, you can compress air and store underground and release it. So that's also another storage mechanism. Then most of the time, everybody familiar with the pumped hydro, right? So you just pump water to a higher potential energy, store there, open the dam and release the energy. Right? So these are all energy storage techniques, but my talk is about this one, battery electric storage systems. So this picture, also everybody should know storage time scale. If you look at hydropower, how long it takes? It takes days or hours, right, to pump your storage time. Even compressed air and storage, that also takes many hours. This is 1 hour border here. Even this, I'll talk about this recent flow batteries of that later I'll talk about. So batteries also, we know, so your laptop, how long you have to charge? Still a couple of hours, right? So still you are talking about little bit, maybe some, if you have a good battery, it can charge in less than an hour. But still we are talking about our scale, right? But these things like supercapacitors, this superconducting energy storage, these things can be stored energy at a much shorter time scale. That's important to understand.
So what's about flywheels for?
Oh yeah, so I had the picture. Here is the flywheel. So flywheel is basically you have very fast rotating drum here. So then when it is rotating, so you have your rotational energy. So suppose if it is rotating at frequency omega, so then this has a kinetic energy of half I omega square, right? So you can have large I, so that's why flywheels are big. So you have to have large I, then omega so fast. So this way you can, suppose if you have something, so you can make this flywheel to store that energy using this kinetic energy. So but that has a lot of other issues. You need to have good bearings to, otherwise they will dissipate energy, right? So some magnetic cushion, so all these things are, this is commercially available flywheels already.
Ребят, меня это на самом деле удивило. Люди запасают энергию, вот в гироскопе фактически заставляют быстро вращаться какой-то груз на подвесе, на каких-то хороших подшипниках, на магнитном подвесе, и таким образом запасать энергию. Я не знал, что так можно. А это коммерческая технология, оказывается. Если у вас много энергии, то можно настоящий успокоиться.
Yeah, so this shows the compressed air, right? So if you have some turbine or something, then that energy you use to compress air and store underground. So when you need, you can release that energy and use it for your purpose. This is the hydropower. So from the lake, you pump water to your dam to here. So when you want, you release it and so superconducting storage also going from superconducting to normal state. Okay.
Ghamini, you know is decline.
Which one?
No is where is it easy to apply this technology?
Where? I mean, the hydropower is wherever you have good rivers and
He's talking about
fly fields.
Compressed and fly.
Or compressed air.
Yes, that's
Oh.
why.
Compressed air, I think is in US they use in many areas like deserts kind of areas. So they can, because you need to have good land area also, right? So, yeah, but they are not very common like hydropower, but they use that. But now I think everybody, that's why, these are very difficult, that's the important question here. They all involve a lot of work, right? It's very expensive. Hydropower also you have to make dams. If you can make good batteries to store energy, that would be so easy. So that's why people are trying to make big batteries, large batteries, they can store energy. So today we are going to talk about the battery storage systems. So I don't know how people are familiar. For that you need to have something called the rechargeable batteries. Something you should be charged, then you should release, then again charge. So that not only for this energy storage, especially important for transportation, right? If you have electric vehicles or hybrid electric vehicles, that requires a lot of storage requirement. So right now, there are two ways to look at the battery storage system. One is for mobile devices, for your laptop or your cell phone and laptops and things like that. Other one is slightly bigger, that is for Tesla car. You need to have large storage capacity. Then you need much bigger scale to, like if you have a solar farm or wind farm. So when you produce this energy, you need to store it very large. But that one, you don't care about the weight. In a car, you are concerned about the weight of your battery, right? You cannot have huge battery in your car. But in a wind farm or solar farm, you can have huge battery, right? Your weight is not a concern. So that's why you have to think battery requirements in different applications. So I think initially people have done for maybe about more than 100 years, people have developed lead acid batteries. Everybody familiar with lead acid batteries you have in your car? So you have basically one electrode lead, other electrode lead oxide. What is the electrolyte? It's acid, right? It's sulfuric acid. Yeah. So but those are not very high energy. So that's why right now most popular battery system is lithium-ion batteries. So everybody, your cell phone, your laptop, your Tesla car, they all have lithium-ion batteries. So lithium-ion batteries are good, so they are still, you have a limit how much energy you can store in lithium-ion batteries. So already people are concerned to go something called beyond lithium-ion. So because lithium-ion is good, but because of the limitations, everything has a theoretical limit, right? So you cannot go beyond that. So that's why people are trying to look at other technologies called lithium-sulfur batteries, then lithium-air batteries, and also these flow batteries. I'll talk about all these things very quickly. Yeah.
There is maybe one or two Tesla cars
In the whole
Unicef.
Okay, that's good. Yeah. So how many charging stations in Perm?
We have 3 charging stations now. About 2 or 3 maybe.
At home they have some.
At home, maybe they have a diesel generator.
Oh, yeah. That's not a wise move, right?
It's not for us.
Okay, so now if you look at transportation requirement, so for example, let's look at like Tesla requirement. So if you look at lithium sulfur batteries, this energy density is very important. So like I said, energy density is coming in this watt hour, right? But you need to know something called the specific energy density. That means how much energy for a given weight, right? So that's given by this watt hour per kilogram. Right now, this number is about 200 watt hour per kilogram. But what people want to have is 500. That's some initiative called 500 watt hour per kilogram initiative. But maybe by 2015, 2025, they like to have batteries with 500 watt hour per kilogram. Also, not only that, the cost is very high. Right now, 1 kilowatt hour, that's energy unit, right? We know for your electricity bill, how much you pay. Kilowatt hour is only cents, right? These are mostly, here what is mostly hydropower or coal power? Hydropower, right? So we are paying like few cents. But if you, for the transportation, we are talking about, right now, we are paying like $150 per kilowatt hour. But in 2025, they want that number to be at least 60 kilowatt per 1 kilowatt hour. So this is the target, this is right now. The lifetime also, you need to have a lifetime of at least 7 years. Right now it's only 7 years. Even Tesla has, after 7 years you have to replace the battery. That's pretty expensive. So what they want to have is at least 20 to 25 years. This requires about 10,000 times charging and discharging, right? Every time you charge. But these are pretty good, right? How many times every day you charge your cell phone battery? Still, they last for about 5-6 years, right?
Maybe 2 or 3
3 years, yeah. But what you have is about 20-25 years. So these are very ambitious targets. Then the charging rate, that's also very important. Right now, your battery takes a couple of hours, right, to charge. But what you have to have is maybe very fast, 10 minutes. You just plug in, immediately it charges. So that's very important to have this charging time less than 10 minutes. Another thing is right now, lithium-ion batteries are not very safe. Have you heard about these accidents? The airplane, your laptop, yes, yeah, blowing up, yes, yeah. So there are a lot of concerns about this safety. In 2025, maybe to have more safe batteries. So this is very ambitious target. So let me now go through these battery materials we are. So if you look at your batteries, mostly people are actually still trying to do things like fuel cells. Fuel cells, there are some car companies, they want to make cars driven by fuel cells. But fuel cell problem is they are too expensive. Everybody familiar how the fuel cell works? Yeah, it's basically you have to produce the supply hydrogen and oxygen. Oxygen is easy, it's just air, right? But hydrogen is not easy. You cannot carry large hydrogen tanks, right? You need to have some way to produce hydrogen. That's why I can do another lecture on how to produce hydrogen, like using solar cell, solar energy, or catalytic way. So, but biggest problem is when you have hydrogen, the hydrogen, these are molecules, right? It has to become this hydrogen, atomic hydrogen. To do this one, you need to have a catalyst. To become hydrogen to this one, you need to have a catalyst. So catalyst right now only platinum works. Platinum is the best catalyst. So there are some other Yeah, palladium, all something called precious material. They are very expensive. Even something called, there are a lot of research to replace platinum. Still, nobody has come close to platinum. So that's the biggest problem with the fuel cells. But still, I think, but you don't need too much catalyst material. So that's why some people are still optimistic about using fuel cell based cars. So then this is the best bet we have at the moment. So then also supercapacitors, they are good, but they don't have very large energy. But they have very high power. You can charge very fast, or you can release energy very fast, but it doesn't hold energy, very large amount of energy. So this one shows you oh, this one. Yeah. This is important slide. So if you look at this axis, what is this? This is energy axis, right? Watt hour per kilogram. That's the energy. This axis is power. This watt, no hour. So if you look at this one, you can see gasoline. It's very good, very high energy, very high power, right? That's why you are using gasoline for your car. Hydrogen also very good. Hydrogen also has very high energy and power, but hydrogen is very flammable, right? You cannot do it, use it. But if you look other things, batteries, good high power energy, but how about the power? Very low, right? If you look at the capacitors, supercapacitors, they have energy very low, capacity is pretty high. So, but there are other things, like even flywheels also, they have, I think, comparable. They are better than batteries in terms of power, but energy is very comparable. So what, if you use batteries, some people are thinking about combining battery and capacitor to have both advantage, power and energy. So this shows you something. So say battery has only this one, right? Low, high energy but low power. This one has low energy but high power. If you can make hybrid device from these two, you can expect something to get. That's pretty good, right? If you get this one, you have high power and high energy. There's a lot of research going on making hybrid supercapacitor battery material. So now let me get started with. I'll start with. Start with this one. At the moment, if you look at any battery chemistry, so still people use graphite as your anode. I don't know whether they are familiar with. If you take a battery, there are three things, right? Battery has, we call anode. This is the negative electrode. Then we have cathode, this is the positive electrode. Then you have to have electrolyte, this is a solution. Electrolyte. So electrolyte is the one that has the ion. In the case of lithium battery, we have this lithium ion, positive positive ions, right? So these ions can move inside the electrolyte. If you connect this one to
just break it in parts.
That works?
Yeah.
So if you use here, so electrons will move in the outside circuits, ions are moving in the electrolyte. That's how you complete the circuit. Familiar with these words, right? Anode and cathode. So typically anode, these were the oxidation reaction happens cathode is where the reduction in chemistry point of view. So if you look at lithium ion batteries, so graphite is your anode. So you can see here. So but that this axis is the voltage in volts. This is the capacity in this milliampere per gram. This one per gram. So see, graphite has only 372 milliampere per gram. The voltage is close to zero, right? So that is your anode material. So recently there's a company, actually they moved their company from California to Kentucky called Blue. So they are using new battery called lithium titanate batteries. So that has voltage about 1.2. Actually that's bad in terms of voltage, because your real voltage is, suppose your anode has, this is anode, this is cathode. So this is your anode voltage, this is your cathode voltage. When you have the battery together, your real voltage is the difference between the two, right? So that means if this is high, your real voltage will be low. So that means this is not good in terms of voltage. So what you need is your cathode should have very high voltage, anode should have very low voltage. So typical cathode, they have this something called this layered material. There are different, the way battery works, maybe it's better to show this one first. This is how the battery works, right? Suppose this is your anode, this is your cathode, you have the lithium ions. When you charge the battery, charge means what? You plug your battery into the wall, right? So then what happens is these lithium ions go into the graphite layers. So these are perfect, this graphite, between graphite layers, lithium can easily go in. So then you have electrons coming this way. So when you use the battery, that means like here, now I am using battery to power the my computer, right? So you are discharging the battery. Discharge, what happens? This lithium is coming out from the anode and go inside the cathode. So that means cathode also should have nice layered structures. So graphite is ideal. So because when they go in, come out, nothing happens to graphite. So they just let it go in and out. That's why graphite-based batteries last very long time. But you can see the energy density is very low, only 300. So in the cathode side, still you need to have these layered structures, but it's not just the layered, you can have any of these, they call this spinel structure, and there's something called olivine structure, that's how the crystal structure, they all have good kind of space. It's not exactly like this. This is good layered structure, but you can have something like this, right? Still you can have lithium to go. So that's why they have the, it can be spinel or olivine structure. So they are not exactly layered, but they have good gap between them. So yeah.
Хотел пояснить, что тот литий, который ходит туда-сюда, он действительно ходит внутри структуры материала. И графит чем хорош? У него слои есть. Между слоями он легко проходит без разрушения материала. Если вы возьмете что-то с другой структуры, у вас просто образец разорвется физически, будет уничтожен. Поэтому графит хорошо, а другие под большим вопросом. После нескольких циклов зарядки-разрядки они могут просто разрушаться. Вот о чем говорить.
So you can see anode is only this part because low voltage, right? Cathode is all high voltage. Your cathode voltages are typically 4 volts. So anode voltages are something, graphite case is about 0.2 volts or something. Then your difference is good, right? So there are 2 chemistries. One is the insertion chemistry. That's the one goes in, comes out. That's the insertion, right? Or intercalation. So, but those materials have low capacity. See, this has only 300. This one even has less than 200, right? But these are actually not bad. So they have capacity 300. That you cannot change much. But voltage is very high. But there's another chemistry called conversion chemistry. That means it doesn't have to go in and out. They just react and reaction, and we call it alloying and de-alloying kind of thing, right? Those things can have very large capacity, say even up to 4,000. So you are going from silicon, tin, all these have very large capacity. Compared to graphite has only 300, right? So also in the cathode side, these are cathode, this sulfur, oxygen, they are cathode materials, but they are not as high as this material. So there's a new battery, like if you use the lithium sulfur battery, you use this cathode and anode is your lithium. So lithium comes somewhere here, just a lithium metal. But lithium metal is not stable, so not safe. That's the problem. So this material, this typically that's oxide. So everybody working in oxide, we know if oxide can make all these layered, spinel or olivine structures. When Sony made their first lithium-ion battery in 1990, I think. So they used lithium cobalt oxide. This was their cathode. Graphite was their anode. So still people use this electrodes, even if it is low capacity, because they are very good. You can cycle. So there are some modifications. But this one they have improved a lot. So instead of cobalt is not a good metal because they are expensive and also they are not environment friendly. So that's why people try to replace this one using nickel and manganese, and also sometimes they try iron. So, but mostly these 3 materials. You can combine nickel, cobalt, manganese and have less cobalt and more nickel and manganese. This material is called NMC. NMC means nickel, manganese, cobalt. What people want to do is more nickel and manganese and less cobalt. If possible, completely get rid of cobalt. Remember, this is if you read the battery literature, NMC sometimes this always come across NMC material. So yeah. So this shows you how to calculate. I think everybody has a homework. You can do this one. When lithium integrates with in graphite, eventually it makes LiC6. This means for 6 carbon atoms you get 1 lithium atom. So from this you can calculate what is your charge capacity, right? You know the atomic number. So carbon has 12, right? So then we know the Faraday constant, so because that involves the electric charge and the Avogadro number. If you calculate that, comes to 370. That's very easy to calculate. Right? Each lithium ion, you get 1 electron So then you know what's the charge, right? So then if you calculate per gram, you can easily calculate this coming from this 12 is the atomic weight times 6 of them, right? That's where 72 comes here. So please do this one as a test. So you can see that voltage is only 0.05. That's good, right? But in the cathode side, your voltage is about 4.25. That's why you have a good number here. But now, this is the original Sony battery, but now people use this NMC material. So then, since this one has these large numbers, why can't you use this one? You can, if you want to increase the capacity, you should replace graphite with some of these, right? So this problem is, they are not intercalation, right? They are reaction. When that react, its volume expands huge. So for silicon example, the volume expansion is about 280%. That means that's huge, right? So first cycle, very good capacity, expand, when you take it out, it just collapses. I have a nice video here. Yeah, this one tells you. Yeah, here look at these numbers. For this graphite carbon, this is 372. Tin has about 1000. Silicon has about 4000. So everybody will jump to use this one, right? That's the best material. But if you use this one, this is what happens. So look at the picture in the right. This shows you silicon nano particle. They did in situ lithium insertion. You can see lithium comes, so then just so when lithium is coming in, you can see it's expanding, expand, and just collapse. So that's why you cannot use silicon in this one. But people are doing a lot of other things to make silicon nanowires. When you make a nanowires, then it doesn't expand this way, mostly because of this one-dimensional nature. So you can reduce the expansion, but still they don't work after several cycles. A lot of things. Then some people use silicon nanowires and put silicon nanoparticles onto that one. So then silicon particles will take some of the stress, so the wires will stay intact. So but still they are not practical. Oh yeah, this is in situ TEM, yes. So nowadays, just recently we bought that one. Inside the transmission electron microscope, you have a special holder. So you can do the electrochemical analysis inside. That's very common now. It's very expensive though. Okay, so in terms of so right now what people are doing, you can see in terms of the cathode material, you can see this is the initial Sony work, right? Lithium cobalt oxide. This is the capacity about 150 as a function of number of cycles. Even after 50 cycles, that's pretty good, right? So if it's a bad battery, it will just go to zero. But if you mix with other things like even lithium manganese oxide, that's not good, so it's going down. But if you put all lithium, manganese, nickel, so you can see you can get even close to 150, right? Something it's very stable. So we recently submitted a paper, we get close to 200 with different NMC concentration. So a lot of work going on in this direction to increase the cathode capacity. But anode still, there's no right material except graphite. But now some new work on this lithium titanate. But lithium titanate problem is your voltage is, because anode voltage is high. So that means your difference is smaller. But there's one advantage when we use something close to this 0 volt. Suppose graphite has about 0.5 volts or something. This lithium titanate has about 1.4 or something. This has some advantage because it's not close to lithium potential. When it is close to lithium potential, what happens is something called lithium plating happens. Lithium metal will plate on your electrode. That's bad, right? Lithium, then it can short it. So, but this one, since it is away from that potential, lithium plating is not very common. That's a good thing. So, in terms of anode, you can see carbon. Carbon is 372, right? But still very stable. But now people are using recently silicon, tin. They show now large numbers, but they go down very quickly. But recently people have done this iron oxide nanowires, then they mix with carbon, so they can get stable like 800. So that's pretty interesting. So tin is very good, but you can see how going down. See, if you look at this one here, tin has very high capacity, right? Yeah. Tin has about here, tin has about 1000. So, but if you use it in this battery, see, first cycle has about 1000. Second cycle, it's going down like crazy. That means it doesn't work, right? Because volume expansion. But if you do some tricks, you can make it stable a little bit. So now you can see some other things like molybdenum, carbon, and you can make about 400, 500 stable. Lot of work going on in this direction to make high anode and high cathode voltages. We are doing a lot of work using tin dioxide, decorating with tin and so many things. But yeah.
What about nanowires?
Yeah, that's
Is it only research or you can buy
Yeah,
this
yeah. Still, I think nanowires, very few companies they can make large quantity of nanowires. That's the problem. So material, because I don't know if you are familiar with how they make the batteries. So typically, when you make the material, first you need to coat it onto some like a long sheet. For that you need to make a kind of slurry. Like suppose if I take the graphite, so you have to mix with some kind of organic solvent like NMP kind of. So then something called Dr. blading. You have to make a very thin coating of that material. Then you have to bake it and do a lot of things. Then after that you have to, if you use a coin cell battery, you have to cut pieces. If you have a pouch cell, you have to, you call the slit it. You have to slit it. So then you have to assemble that one. So that means you need a lot of materials. You cannot just make small quantity and make a commercial battery. So you need to have large. Graphite is so, you can just dig graphite from the ground, right? So they are good graphite. So we have to, it's highly available. So these things of NMC also we can make in large quantities for the core precipitation technique. So some of these nanowires, they are good in lab research, but it's not large scale production. That's the problem.
It's very perspective to research nanowires production techniques.
Oh yes. Actually, we have one of our professors. He has a company called Advanced Materials. They are making nanowires. They can make few grams. Still, yeah. that's still big. Most people make milligrams. Okay, so this is also important thing to remember. The electrochemical, this half cell potential. So you can see lithium has the largest negative potential. That's the most electropositive material, right? So that's about -3. This one, chlorine, has highest positive voltage. That's the most electronegative element. That's why we use lithium CFX batteries, right, to get there, but they are not recyclable. But compare related to this zero hydrogen potential here. So from here you can calculate what your potential would be. Before you do, you need to know this voltage. This you can easily calculate from something called Nernst equation. In chemistry we learned. So that involves Nernst. In chemistry they use Nernst equation. That's looking at the this is given by this Faraday constant, then logarithmic this your product concentrations, whatever. I think chemistry people know the Nernst equation.
Это все физики.
Maybe they use different name. So another important thing is want to talk is it's a really important point. I forgot which and work on this batteries. Anyway, so this one also shows you some good picture, capacity versus voltage. You can see all the NMC materials are here, right? 4 volt. These are all these different manganese, graphite is here, so tin, all these things. You can see the lithium. That is very high, right? But you cannot use lithium as your one of the electrodes. So not safe at all, right? But that's why when you study your some anode material, what you do is you first test it with lithium. This is very important for anybody working in the battery area. Suppose if I want to use some anode, you have to use that anode with lithium foil. So this is called a half cell. If you want to use a cathode, you always study your cathode with lithium. Right? Now, if you want to use the full cell, you have to use this one and this one. Right? That's how you make your real battery. You have your anode and your cathode. So when you use lithium, that's fine because you have a lot of lithium. So when you use here, you have a lot of lithium. But if you use these two, where's the lithium? That's where the problem is. You have to lithiate one anode. That's why if you look at this cathode, everything is lithiated, right? So you cannot use like this. Your graphite doesn't have any lithium. Other electrodes should have enough lithium. So you have to make sure you have enough lithium in one of the electrodes, because then you have enough lithium. There's some lithium in the electrolyte, but you need to have enough lithium coming here and coming here. So either you have to lithiate this one. Most lithium-ion batteries, cathode is we call the pre-lithiation. You have to lithiate,
You need to add lithium to the cathode?
Yes, yeah. So that means your compound is a lithiated compound. So that's why one electrode here is fine. We have lithium, infinite supply of lithium. But when you put the two metals together, that's the real battery is this one, right? This is how you screen your material. Suppose if you give me some material, if I want to use as anode, first I do is what? I test with lithium. That's the half cell. So then I want to test in a full cell, I have to use this way, but in that case you need to have one electrode already pre-lithiated. They call the pre-lithiation. This is very big, difficult problem. How to make the, for example, we did, one of my students, he did next one I'm talking about, the lithium sulfur battery. Everybody is now familiar with the lithium ion battery. So, what the requirements and so, but people think lithium ion battery has its limitation, right? So now they are looking for something more than lithium ion battery. That's why they want to go for that, remember, conversion part. So not the intercalation part. So there you have sulfur, oxygen, like a cathode. So this is why people use something called the lithium sulfur battery. So in this case, again we test this one with lithium. So when this happens, your capacity should be about 1600. When you make this is a conversion, right? Not insertion. So when this happens, you have sulfur. To begin with sulfur, when you react with lithium, it makes this one. So this capacity, the voltage is about 2.2 volts, not 4, still not very big, but capacity is about 1600 milliampere hour. That's pretty good. So, but problem is, before it makes this one, it has to go through lot of steps, like it makes Li 2S6, then it makes Li2S4 and Li2S2, then it goes here. So it doesn't go directly from here to here. It has to go, you can see here. It goes, this is the initial sulfur, then it has to go 8, 6, 4, eventually it makes this one. These things are dissolving into the electrolyte. That's bad, right? When these are formed, these are solid. Sulfur is solid, this final product also solid. These are, we call the polysulfide. They dissolve into the electrolyte. That means you are losing it, right? So that's the big problem. So these things, they can even go to the other end. We call the polysulfide shuttling. So this longer ones come here, then they become short, then it goes to other one. So this is the biggest problem for lithium sulfur battery.
Is it rechargeable?
What's that?
This battery rechargeable?
Yes. So then, yeah, from here, then you can go back to S8. So, but one thing you can do is, suppose this is your sulfur, you can have some protective layer here, right? So that's the opportunity. We put titanium coating here, but still lithium can go inside here. We need to have lithium reaction, right? But this one, when they are formed here, they cannot come out. So they can, but still it worked pretty good, but still some issues there. Yeah, actually Luisville got very high capacity, about 1000, very stable for 100 cycles. So that's, I think we have a good, this is called the cathode. So we have a good half cell results, but now we are putting full cell. So when he did that one, he has to have enough lithium in the anode. So we used something called molybdenum oxide as our anode. That's pretty good anode. We use this one with sulfur, but we have to lithiate this. So we have to have lithiated molybdenum oxide. So he make a full cell with this one. That worked pretty good. He could drive a drone with this battery. So he's right now working on this one. So
Did you test that?
what's that?
Did you test that?
Oh yeah.
How long drone?
Oh, probably there's this group of Indian students. So he was helping them to use that battery. I think they could hold for maybe at least half an hour. He made a large something called the pouch cell. So there's a lot of research going on in this lithium sulfur, then also lithium oxygen batteries. Lithium oxygen. Remember, there was a slide, oxygen also in that category, right? If you come down here. So sulfur here, that's a cathode. If you take oxygen, it's much even higher. So, but oxygen also has a lot of other issues like some moisture and those kind of things. So these are still in research state, so still nothing much is happening yet. So finally, how much time we have? Okay.
We have 10 minutes.
10 minutes, okay. So finally I will talk about something called the new thing called the flow batteries. So this is a new idea. So only difference is now, so this is your anode and cathode, right? Everything happens at the electrode. So then afterward, electrode will get consumed, right? So they become bad. So in the flow cell idea is these material, they are in the storage tank. Outside storage tank, we have the material, you just pump into the cell. So here you have only two, we call the current collector. Remember, when you make the battery, typically you have to have a conductor, right? To take the current out. So usually we use aluminum for cathode and copper for anode. Reason is anode potentials are very low, right? At low potential, aluminum can get oxidized. For cathode works at high potential, so copper gets oxidized at high potential. So that's why typical cathode we grow on, coat on aluminum, anode we grow on, casting on copper. So then we can take the current out, right? So that's how, if you look at any battery, that's how anode and cathode are done. So then the material is here, right? This is your material on the current collector. In the flow battery, you only have current collector here. So this material, they are coming from outside tank. So you have to pump these things over in here. If you look at, so this is what you have is only this anode current collector. This is the current collector. So the electrode materials you are just, so you can see this is the tank that has this, we call the analyte. So you just pump into this one. Here, catholyte, you just pump into this one. Then reaction happens in the solution. but the charge is taken out from the current collector. So that means, like here they don't get consumed. You always supply your electrolyte, your electrode material from outside tank. So that's the advantage. So, but you can see you need to have some energy to pump. What's that?
Some space.
A lot of space. Yeah, these are like, we are talking about this tall, large tanks. But this has, I think, longer charging time, but it can hold charge for a long time. So this is a new trend. There are different. So only thing you have to have is this should have some redox couple. One has to have one oxidation state higher than other one. For typical materials, they use vanadium. We have vanadium 4 plus and vanadium 5 plus in one side. Other side they have vanadium 3 plus and vanadium 2 plus. Because you need to have some conversion, right? This oxidation state. So these are some of the things people. Right now this battery is very popular. Vanadium. So you can see this vanadium going from, okay, if you look at it, this is 4 plus to 5 plus, this one is 2 plus to 3 plus, you can see the reaction. Still you need to have a membrane, only one kind of ion can go from one side to the other side. But this, already they have large flow batteries commercially available. So there are several companies making these batteries. Not only vanadium, they also have redox couples like iron chromium. You have one iron 3 plus, iron 2, 2 to 3, and then iron titanium, bromine sulfur, iron vanadium. There are many flow battery. We call the redox couples. Okay, so I'll just stop here. So this shows you that time scale. You can see lithium-ion battery is still is pretty large charging time, but the power is pretty in this range. So hydropower has much higher power, and your charging time we are talking about. So this is actually, if you look from here, it's like 100 hours here. This is our time here. Okay, so I'll just stop here. So just give some idea where the battery technology is. So what we need is, everybody is looking for this 500 watt hour per kilogram for less than $60 per kilowatt hour. That's what
It's our aim.
yes. But this is a full cell we are talking about. When you put real cathode and real anode. Remember, typically, if you talk about everything, when you look at this one, these are half cell results. These are so all these are half cell tested with lithium. But when you put for real battery, then what you have is, so this is a full cell. Suppose this is your anode.
Real battery, no.
Yes, yeah. Real battery, then your real capacity is having like two parallel capacitors, right? So that's ideally it's like 1 over C equals 1 over C1 plus 1 over C2. If you have two capacitors in series, you get this capacity, right? So you can see how the real number, but typically this number is against lithium. The other one, even here, this number is against. These numbers are all with respect to lithium. But when you put the two together, you get capacity as a series capacitance, right? But remember, when you do that one, you have to make sure you have enough lithium in your system. That's the biggest problem. When you test with lithium, fine, because lithium metal has enough lithium, right? Now when you have cathode and anode separately, you have to make sure one electrode is perfectly lithiated. There's a lot of research activities in battery area. So, okay.
Ребят, вопросы?
Yeah, any questions? On physics? Yeah.
And for flow batteries, how fast should we renew the cathode and anode?
I think that they can run for weeks without any replenishment. Yeah. The only thing you have to do is just put new. You don't have to interrupt anything. Yeah. Like if you have a real battery, if something is bad, you have to destroy it, right? But here we just go a little more analyze.
So it's a question of resources.
Yes, exactly. Yes. Because also we don't care about the weight, right? These are for stationary applications.
We're talking about transportation.
Yeah, transportation. There's no way you can use flow batteries, right? Because they are too big. Right? Transportation right now, hope is lithium-ion batteries. So then maybe if lithium sulfur or something, if that can mature, that can be used. Also, like Japan, they are seriously working on fuel cells. Even platinum is a little expensive, but still they are working on fuel cells. I think already fuel cell use cars are already, even in US, I think there are some. So Japan, Germany, they have already hydrogen filling stations, right? When you use the fuel cell, you need to have hydrogen supply, right? So they need to have hydrogen stations. So you have to, in Germany, even California also they have several.
Маленький комментарий по поводу гибридной батареи. У профессора Гамини есть направление, которое посвящено батареям, и есть направление по поводу суперконденсаторов. И он думает соединить одно с другим. Например, почему у нас в машине такие...
Oh, you mean little bit about supercapacitors?
Supercapacitors and batteries hybrid.
Yes, yeah.
Почему в машине такой большой тяжелый аккумулятор? Потому что надо крутить, когда стартуешь с большим током, а потом столько не надо. И можно соединить, суперконденсатор будет заводить машину, а потом небольшой аккумулятор будет использоваться уже в движении. И все это можно сделать гораздо компактнее.
Yeah, supercapacitors is all about area. Right? You have large surface area, because remember, a lot of physics students, right? So capacitance is given as this one, area times your dielectric constant divided by the separation, right? So if you can make area very large and separation very small, you can make a large capacitance. Typically if you use this is for electrostatic capacitor, right? If you have two plates separated by D and area A, right? So that's the capacitance. But if you have electrochemically, you have these ions and negative ions. So this is the positive negative charge, right? Here, this separation is only angstrom, right? So that means D is very small, that means your C becomes very large. Same thing from other side, you have negative charges and positive charges. Again, this space is separation is small, that's why you get large capacitance. Then to increase A, you make nanomaterials that has very large surface area. Like Alex did some work, we had the surface area about 1,000, right? Yes, about 1,000 meters square per gram. That's some nanocarbon material. So that means A is large. Then we can make, I think the material he made, we had about 150 farads per gram, right? It's close to, then you improved it to about 200, right?
Yes.
So that's huge. Typical electrostatic capacitors, what is the capacitance? Typically microfarads. If we use electrostatic capacitors, we are talking about microfarads, picofarads, maybe best, maybe millifarads. Here we are talking about farad. So that's huge number.
Gamini, for supercapacitor should we combine electrical double layer capacitor plus pseudocapacitor?
So yes, yeah.
Where is it in this scheme?
Not in this one. Typically, if you look at this, this is called the electrical double layer capacitance. But this is the double layer, right? So then if you look at your current and voltage, they are pretty much like this. So but ideally it looks like a little bit like this, right? So but if you can make some charge complexes, we call that from redox centers, then you have some additional reaction, redox couple contribution. So that is the pseudo-capacitance. When that happens, this one will do like that. So you get some extra capacitance from that. So that's how we get large capacitance. So this is called pseudo-capacitance.
Все.
So, yeah. Yeah. So that will make your capacitance, like Alexei, he mixed this carbon, nanocarbon with some conducting polymer. So conducting polymers are donating electrons to the carbon nanocages, so that will make this some conjugate system. So that's why we get close to like 200 some farads per gram. I won't finish that paper. So typical capacitor looks like this. If you look at voltage versus time. The charge, discharge. Right? This is very short time. Maybe it happens very fast, right? So in your next cycle, like that. But if you have pseudo capacitance, this becomes a little bit non-linear, like that. Because this part is coming now. Okay, I'll stop here.
Okay, thank you very much.